to find the electric field of this ring of charge that has a radius r, the total charge q, along its symmetry axis with distance z from its center. Again, in order to do that, we take a small piece of that which has charge dq. This creates an electric field dE at this point. Now we need to integrate the dE as vector. Charge element goes around this disk. And you see that if you take another one that is on the opposite side, it creates a field this way, right? We just need to find Ez, which means that the electric field component along the z-axis, because the other components, when you integrate, they cancel each other out. I can show that mathematically, but I think it is easy to see, right? Do you see that when the electric fields are like this, all the parallel components are perpendicular to z, cancel each other. Only the z components survive and add up, right? And Ez will be integral of dE, dEz, which is integral of dE times cosine of this angle. Right? So I need to write dE and cosine theta all in terms of the parameters that we have in here. See, this distance is r, the radius. This distance is z. Let's call this r. dE magnitude is what? Is k dq divided by r squared. And what is r squared? You see that there is a right triangle here. One side is r, capital R. The other side is z. The hypotenuse is r. So r squared is equal to r squared plus z squared. And what is dq? We keep dq for now. What is theta? What is cosine theta in this? You see, if this is theta, this also is theta, right? What is cosine theta in there? Cosine theta is adjacent, which is z. Let me put that on the other side so it's more clear. Is z over r, isn't it? So it's z over square root of r squared plus z squared. So Ez will be integral dE, which is k dq over r squared, which is r squared plus z squared, times z over square root of r squared plus z squared. Does it make sense? Check if everything is correct. So k dq over r squared times cosine theta. And now, I want to bring everything that's constant as this dq goes around. Everything that's constant should go out of the integral. What are constants? Is k constant, right? Is r constant? Is z constant? Is this the r? Everything is constant. Everything comes out. You see, the integral is very easy. So it becomes k z divided by r squared plus z squared to the 3/2 integral dq. What is the integral of dq? Total charge q, right? So Ez, which is the total electric field will be K Z Q, or K Q Z, divided by R squared plus Z squared to the 3 half. Very easy. You don't need to do really any integration. Now I would like to do something more challenging. Suppose this is not a ring, but it's a disk. It has a surface charge density sigma. So if it is it looks the same, but this one is not hollow. It's a disk with total charge Q, but surface charge density sigma. A sigma is surface charge density, or for charge per unit area. Or because you know if the total charge is Q and the radius is R, sigma will be the Q over pi R squared. And now again we want electric field along the axis of this disk at distance Z. So how do we do this? If you want to be, mathematically very rigorous, then you have to take a small piece of this, calculate the electric field of that one, and integrate over the disk. But because we have this result for a ring, you can split that into small rings. And then for each ring, you use this result, and then integrate over the rings to go from the center to the edge. Right? So that's what I'm going to do. So if you split this, let me draw another figure which is more clear. If this is the ring, you take a small piece of a small area with the radius r and the thickness dr. And dr is so small, so this is dr. Because dr is very small, this is like a ring. We know how to calculate the electric field for that. And then once you have for this one, you add all the contribution of different disks, different rings to get the whole disk. If this is our element, it has a charge dq, and we know that we know what kind of electric field it creates. If it has a charge dq, what is the electric field of this one, which is dE, in this case, dE? What is the electric field of that one from that equation? It says Kz, this is this charge, this is its radius, and this is the distance from the center. Can you tell me what dE is now? So K, Z is the same Z. K, Z, and the charge is dq, and the radius is this little r instead of capital R. So r squared plus z squared to the 3 half. This is dE for that ring. But what is dq? How much charge does it have? Because we're going to integrate over this and over r from 0 to the edge of this, which is capital R. We need to write everything in terms of r and constants. How do I write dq? That's the the only tricky part of this. How to write dq. It's not that tricky, but if you think about it, you can come up with it very easily. Yes, please?
Do you take the area of the bigger circle and the smaller circle and subtract them?
That's, you get, if you subtract those, you get the area of that strip, yes. So what do you do with that?
Oh, like what's the area?
What is the, we want to find dq. You want to find, you're on the right track. You find the area of this. So you know that the charge is related to the area. How is it related?
Oh, sigma.
Sigma is dq over dA, right? Means the charge per unit area. So it has dq over dA. So we can say dq is equal to sigma dA. Let me call it the area. What is dA? How do you find dA? You said you find the area of the larger circle and subtract from it the area of the smaller circle. You can do that, but there's a faster way to do this. You can cut this and open it up. How much area do you have? One side is the circumference, right? The other side is dr. You have 2 pi r dr. So dA is 2 pi r dr.